Hey everybody. All right. Just to talk a little bit more about the binomial stuff, I'm going to elaborate a little bit on the connection between the Bernoulli and the binomial. This is going to be important on the final because as I'm going through the distributions, it's important to see how each is connected and how each solves a problem that the other one has. So I mentioned in class that the big drawback about the Bernoulli is that you can only work for one trial at a time, right? So if I have a random variable x distributed Bernoulli, right? So this means x, random variable x distributed Bernoulli, where the probability of success p, right, is given. You have to know that going in. So we define that, right, where x can take two values. X is equal to 1 if success, and x is equal to 0 if the trial fails. And you'd have to define success and failure yourself, right? So in the examples I did in class, it was you have a success if you flip a coin and it comes up heads, and you have failure if it comes up tails. Could also be roll a dice and it comes out to be a 4, that's a success. Failure is if it's equal to any other number but 4. All right, so you define it that way. And then the probability distribution, right, the way we find the probability of each outcome is through this equation. Right, so it's p to the x, so the probability of success raised to the x times 1 minus p to the 1 minus x. So the thing is that we can actually construct the binomial distribution from the Bernoulli as long as we assume two things. We have to assume that each trial is independent, right? So basically, if we want to be able to look at the probability distribution where each individual trial follows the Bernoulli distribution, but we want to know how many successes are over multiple trials, we can find those probabilities using a binomial distribution as long as we assume that each trial is independent and each trial is identical. In other words, within each trial, the probability of success p stays the same. So how do we get there? How do we make this happen? So what I want you to keep in mind before I go forward is just what the formula for the binomial looks like. So the Bernoulli is that little equation of p to the x times 1 minus p to 1 minus x. The binomial distribution is n choose k times p to the k times 1 minus p to the n minus k. Where in this case, n is the number of trials, k is the number of successes, and p is the probability of success, just like it was for the Bernoulli. And then what happens is that up here, you're just going to write, if you have a binomial random variable, you change this to write x is distributed binomial with n trials and p successes. Or sorry, the probability of success is p. Okay, so like I said, each individual trial is Bernoulli, and we're able to scale it up this way because we assume that each trial is IID, right? Like it's independently and identically distributed. I talked about IID in class on Thursday. So if you read the lecture slides or you came to class, it should be fairly clear to you what this idea means. But how do we get from that little equation to this more complicated one? Let me show you by means of an example, and I think it'll be pretty clear what's going on. All right, so let's do a very simple example of flipping a coin 2 times, right? So you can define x1 as being outcome. Flip coin, you get heads, right? So this is the first time you flip the coin, so you get a success. And the second event is you flip a coin the second time, you get a heads, success, right? So this is first trial and second trial. And so you already know what that sample space looks like, right? It's S equal to HH, HT, right? TH and TT. So those cases, these outcomes where x1 is going to be equal to 1, right, are going to be this instance and this instance, because the first coin flip is heads, right? And the two trials where you're going to have the second come up ahead, it's going to be this one and this one, right? So you, in both cases, the probability that you're going to have at least, the first head be a success is 1/2, right? Because it's here and here, and the probability that the second head is going to be the second trial is going to be a success. In other words, the second time for the coin to get a heads, it's going to be equal to here and here. All right. So how can we then find the probabilities of getting successive successes, so to speak? In other words, multiple successes or one success or no success. And how does this formula give us that information? So the way to think about it is that, remember the basics. So a very basic case would be to say, I want to know the probability of getting a success on both trials. So it's a probability that x1 is equal to 1 and the probability that x2 is equal to 1. Now remember I said that each trial is independent, right? And when it's independent, what we can do is just multiply these probabilities together. Okay. Now remember from what I said before that because each trial in itself is Bernoulli, I can use the Bernoulli distribution to find this and the Bernoulli distribution to find this. All right? So going up here, I can write, I want to find this out, x1 equal to 1 times the probability of x2. You guys aren't going to be able to see that. So let me write it a little bit further down. I think that's clearer. So it's the probability that x1 is equal to 1 times the probability that x2 is equal to 1. So it's this Bernoulli trial times this Bernoulli trial. So the first, and they have the same probability of success, right? I'll just call it P for now. I'm not going to put in the 1/2, I'm just leaving it as P, and you'll see why in a minute. All right, let me keep this clear. All right, good. Okay. All right. So this probability, right, going back to Bernoulli, is going to be P to the 1 times 1 minus P to the 1 minus 1. Okay? I'm going to multiply that by what this probability would be equal to in the Bernoulli trial. So it's P to the 1 times 1 minus P to the 1 minus 1. All right? Now when I multiply all this together, I'm going to get P squared, right? P to the 1 times P to the 1 times 1 minus P to the 2 minus 2. All right? So if you look back over here, in some respects, this doesn't look that different than what you get when I plug this in directly, right? So if you ignore the n choose k, like I'm looking at 2 trials and k is 2 successes, right? So I have p to the k, so in this case with 2 trials and 2 successes, it would be p squared, just like I get here. And it would be 1 minus p to the 2 minus 2, just like what I get here. And what does n choose k equal to? Well, thinking back to here, right, there's only one way to get 2 successes, right? Heads, heads. And it turns out, when you do the math, right, you guys be able to see this? Yeah. So 2 to choose 2 is 2 factorial over 2 factorial times 2 minus 0. Or sorry, 2 minus 2 factorial. So 2 minus 2 factorial is going to give you 0. That gives you a 1. So 1 times 2 factorial over 2 factorial, this whole thing is going to evaluate to 1. Right? So this would return 1 times p squared times 1 minus p to the 2 minus 2, just like what I get here. All right? So far this might not seem very remarkable, but I think it'll become clear about what exactly the power of this formula is when I look at the cases of just one trial, one success. All right, so check this out. So if I'm interested in the cases of two trials, one failure, one success, I have two ways I can look at that, right? So let's say first I'm interested in the first trial being successful and the second trial failing. All right, they're both Bernoulli. All right, so they're both Bernoulli. So now this is going to become p to the 1 times 1 minus p to the 1 minus 1. That's that first probability. And this is going to be p to the 0 times 1 minus p to the 1 minus 0. All right, so check that out. So when I simplify this down, right, p to the 1 times p to the 0 is p to the 1, 1 minus p to the 1 minus 1 times 1 minus p to the 1 minus 0. This is going to be 1 minus p to the 2 minus 1, right, which is just going to be p times 1 minus p, right, and they're both raised to the first power. All right, so that's not too complicated, right? Again, this is just a product of two Bernoulli trials, and I get basically p times 1 minus p. All right, now if I look at this flipped, right, like I'm curious about what happens if instead of the first trial being a success, the first trial fails, but the second trial succeeds. What do I get? So this is going to become a 0, and this is going to become a 1. All right, let me draw this a little bit better. Okay, yep, that shows up. All right, so this is going to become p to the 0 times 1 minus p to the 1 minus 0. So that's my first Bernoulli probability. My second Bernoulli probability is p to the 1 times 1 minus p to the 1 minus 1. All right, so then when I multiply these values together, I get p to the 1 times 1 minus p to the 2 minus 1, which is just p to the 1, 1 minus p to the 1. In other words, I get the same probability back whether I put in the first trial being a success and the second trial being a failure, or if I flip it and have the first trial be a failure and the second trial be a success. I get the same thing. Now the reason is that if you look here, right, the sample space, there are two ways, right, this one and this one, to get one failure and one success. So if you think about it, if you remember from what your previous classes said and what Mike said, the power of this n choose k formula is that it tells you all the ways to get one success from two trials, regardless of order, regardless of whether the success comes first or it comes second, it doesn't matter. So in other words, what you want to do, and what this is going to say, is that because these two things from the probability point of view are returning the same thing, right? Like two trials, one success, you multiply it together, right? Like you're going to say the first was p squared, but I have two different kinds of ways of getting p times 1 minus p, right? And turns out when you do 2 choose 1, it's equal to 2 factorial over 1 factorial times 2 minus 1 factorial. So it's 2 over 1 times 1, so it does equal 2. Okay? All right. And if you were to go ahead and do the very last combination, right, which is both trials be failures, it turns out what you're looking at is 2 trials, 0 failures. 2 choose 0 is 1, just like what we have here, right? Like, there's only one way to have 2 failures and 2 trials, not just TT, right? And when we do that probability, it's p to the 0 times 1 minus p to the 1 minus 0 times p to the 0 times 1 minus p to the 1 minus 0. And when you do that out, it's p to the 0 times 1 minus p squared, right? If you look here. So if you were to look back here, again, remember 2 choose 0 is 1. P to the 0 is p to the 0. And 1 minus p to the 2 minus 0 is 1 minus p squared, just like you would get here. So in other words, the point of all this is to show in a very direct way that the binomial is simply the direct product, right, of taking all these rules I've been teaching you about independence and about the power of having identical trials, and saying you can get this distribution by very literally multiplying together all the different Bernoulli trials you're going to do, and then group them, right? Like group them by all the times that you get the same thing out. So in other words, right, like when we did this, we twice got this. So instead of writing, if I wanted to write out the full sample space, right, like if I want to write out the full sample space, let me get rid of all this. And going back to the sample space I wrote here, very literally, what I got back was this was p squared, right? Because the probability of getting the first h was p, the second h was p, it's p squared because they're independent. This was p, 1 minus p. This turns out to be also p times 1 minus p. Remember, because it's multiplication, the order doesn't matter. And this ends up being 1 minus p squared, right? And if I want to prove that this exhausts my probability space, the condition for that, right, is that like the sum of all these things has to be equal to 1. So I can test that by just saying, okay, p squared plus p times 1 minus p plus p times 1 minus p plus 1 minus p squared. Right? A very simple way I can make this a little bit easier for myself is just writing this as 2 times p 1 minus p. So that's what this n choose k thing is doing for you. Instead of having to write out all these probabilities and add them together, it's telling you right away what you can just say, this appears twice, right? Or for more complicated times, sometimes things will appear 3, 4, 10, however many times. It just makes it easier. Right? Okay. So, turns out when you do this, p squared plus 2p 1 minus p, you factor out the square so that it's 1 minus 2p plus p squared, right? Turns out that when you do that, here's what happens. You also should factor this out. So let's factor that out. You get p minus 2p squared, right? Like I distribute this 2p through here. Oh, look. All right. So right away, you see that this cancels, and this cancels. I have 2p squares right here, and negative 2p squared right here. So these cancel, and I'm left with just 1. All right? So if you don't believe me, do it yourself. But you can see that when I add these all up, turns out they're all equal to 1. All right. Turns out when you add up all these things here, right? So these are my probabilities that I got out of my Bernoulli, and then I add them up here, and I know that I can just multiply this by 2 because that's what this n choose k thing tells me. Then when I do it all together and I add them up, remember, a condition on a probability space for all events that exhaust the entire probability space that are disjoint, right, is that they have to be equal to 1. So each of these events is disjoint, and they exhaust the probability space, so they have to be equal to 1. And when you do it all out, that is exactly what they're equal to. It's all equal to 1. All right? So anyway, that's what you need to know for all this. I hope that it's very clear after this video exactly what the connection is between the Bernoulli and the binomial. I'll see you in class on Tuesday.